Lesson 9. The work of moments. The work of healing and restoring moments, determination of the minimum overturning moment. The moment is equal to the product of the force and the arm. The displacement of the ship D is taken as the force in the stability formulas, but the arms, depending on the task, are both vertical and horizontal. Why is stability divided into static and dynamic? Due to the behavior of the vessel under the influence of these forces. Static is a constant or slowly increasing moment, towing. Dynamic is a moment that is growing rapidly and appears suddenly, wind squall. Statics and dynamics, with the same force impact, will differ in the nature of this load over time, quickly or slowly. The load is considered dynamic if it rises to its maximum value 10 times faster than the free healing time of the ship on board. The healing period is divided by 4. How is the healing moment graph depicted on a static stability diagram, SSD? In different sources, this is either a straight line or a slightly damped curve. For the convenience of practical calculations, a straight line is most often used, and I leave it for animation. By the way, it is impossible to say from both graphs which moment is static or dynamic, only the value of the moment, or its arm. At what angle of heel will the ship roll under dynamic wind squalls? This can be determined from the condition of equality of the work of the healing and restoring moments. To do this, it is necessary to draw an additional vertical so that the two cut-off areas S1 and S2 are equal. The red triangle S1 is the work of the healing moment. The blue triangle S2 is the work of the restoring moment. The darkest trapezoidal area is common with these figures, so it can be excluded from the calculations. There are two triangles left, red and blue. If the areas of these triangles are equal, then the work of these moments is equal. This triangle equality rule should be understood and memorized. The vessel, under a dynamic gust of wind, will list at an angle cut off by the vertical line. Here the dynamic healing angle from the gust will reach 29 degrees. The squall has passed, and the wind is blowing with uniform force. The ship will get a permanent, static, list of 14 degrees. It can be seen from the animation that with the same moment value, the dynamic heel angle is twice the static one. The area under the static diagram is the stability margin or the potential for the work of the restoring moment. Part of this area, work, was eaten by the healing moment. But the remaining segment on the right is the reserve of dynamic stability, the potential of the restoring moment. Let's play this situation in dynamics. Under a sudden squall, the ship lists sharply to starboard to 29 degrees. The restoring moment does not keep up with the healing moment in time due to the laws of inertia. At around 29 degrees, the restoring moment catches up and overtakes the healing moment and is already greater than the latter, so it quickly straightens the ship. According to the same laws of inertia, the ship misses the points of equilibrium of moments. Further damped vibrations and the ship calms down on a static roll of 14 degrees, when the moments are leveled. The conclusion is simple and obvious: the dynamic force is twice as strong as the static one, which means it is twice as dangerous. In this example, we, for a given healing moment, found the angles of dynamic and static lists. In the inverse task, finding the healing moment, the dynamic list angle is first set. Then, by the position of the vertical line, according to the triangle equality rule, the healing moment is found. When will the margin of dynamic stability end? When the areas of healing and restoring moments will be equal. Here, the healing moment will reach the minimum capsizing value, and the maximum dynamic list will be 72 degrees. Let's calculate the minimum overturning moment. If the z-axis is in moments, then the value is simply taken, but if in the arms, then the moment arm is first taken. The moment is equal to the product of the force and the arm, where the force means your current displacement d equals 3,212 metric tons. When taking measurements, we follow the golden rule: consider yourself closer to danger. 72 degrees is an unthinkable roll in practice. Our left breast has long been out of the water and the buoyancy force B is moving back, to the left. But this is how the minimum overturning moment is determined. Any excess of the heeling moment will result in an overkill. And if the heeling moment weakens, then the restorer will cope with the dynamic listing and the ship will level out through damp rolling, until it settles down with a static list, approximately 27 degrees. The minimum capsizing moment for the vessel with this cargo is determined. The squall affected the ship with zero heel, those. The minimum overturning moment was found from the straight position of the hull. In the IMO Code for Intact Stability, 2008, tightens the control measures for vessel stability and the calculation of the minimum criteria is carried out from the worst position, when the vessel is already heeled in the direction of dynamic load. Why this option is considered the worst will be discussed later. Before I tell you how these tasks are solved on the dynamic stability diagram, DSD, I must warn you that the DSD is not a mandatory in the criteria of the International Maritime Organization. So I'll try to be brief. To begin with, I will demonstrate the work graph of the overturning moment. This is an inclined straight line with a slope equal to the heeling moment or its shoulder. When working with DSD, you can't do without additional constructions. 1. A line segment of 1 radian is plotted on the x-axis. 2. At the end of 1 rad, perpendicularly, the previously calculated heeling moment, or its arm. 3. From the origin of coordinates, an oblique straight line is drawn to heeling moment, this is the work of the moment. 4. The point of intersection of the DSD curve and the oblique straight line is the angle of dynamic list on the abscissa axis for this heeling moment. The inverse task, finding the heeling moment from the dynamic angle of heel, is solved in the reverse order. 1. According to the known dynamic heel angle, the point of intersection of the DSD curve with the work inclined line. 2. From the origin of coordinates, through this point, an inclined straight line is drawn. 3. On a segment of 1 rad, the value of the heeling moment is found. Resume. 1. Dynamic impact is twice as dangerous as static. 2. The method for finding the heeling moment, heeling angles, as well as the minimum overturning moment, is based on the rule of area equality, equality of triangles, the work of heeling and restoring moments. 3. The solution of these problems is easier when working with static stability diagram, and the accuracy is sufficient. 4. The Intact Stability Code 2008 has tightened the methodology for finding areas and incorporated them into the calculation of the weather criterion. More on this later.